Now, all waves have energy, and it shouldn't surprise you that electromagnetic waves have energy because, number one, you see light, so there's some there's some kind of energy going on there, and you've all felt the heat of standing in the sun, so you know that energy is there. And also, we've already talked about how there's energy stored in an electric field, and the energy stored in an electric field, the energy density is half epsilon naught times the electric field squared. There's an energy stored in a magnetic field, and that energy density is the magnetic field squared over 2 mu naught. And so if there's energy in electric and magnetic fields, it shouldn't surprise you that there's energy stored there's energy in an electromagnetic wave. And an electromagnetic wave has both an electric field and a magnetic field, and they're oriented at 90 degrees to each other, but energy is a scalar, so we don't need to worry about direction at all, so we can just add them together to get the energy density of our electric field. Now, for an electromagnetic wave, the electric energy density and the magnetic energy density are exactly the same. So, we can say that this and this are equal. So we can replace this with our electronic energy density and say we've got 1/2 epsilon naught E squared plus 1/2 epsilon naught E squared. And of course, if we add those two together, that just gets rid of the half. So we can say our energy density is equal to epsilon naught E squared. Similarly, we could substitute in our magnetic energy density here, and that will also get rid of this half. So we could also say this is equal to our B squared over mu naught. So that's the energy density of an electromagnetic wave. Now, both fields, the electric and magnetic fields, are sinusoidal. Okay, and we know the average value of a sine wave is 0. However, because it's squared, that kind of makes things positive, and so both the fields are sinusoidal. So when we talk about the energy density of an electromagnetic wave, we often talk about the average energy density. And let's consider, so if we had a sine theta, we know the average value of sine theta is 0. But since we're dealing with the squared, we're really looking at, we want to know the average value of absolute value of sine theta. And the average value of the absolute value of sine theta, it turns out, is root 2. I'm sorry, 1 over root 2. And so that means that the average value of this electric field, or it's called the root mean squared of the electric field. I don't know where that term came from, but the root mean squared is equal to that maximum electric field over root 2. And the same thing, anything RMS, root mean squared, is equal to the maximum value over root 2. So then the average value of the electric field is equal to epsilon naught times the root mean squared value of the electric field squared, which is equal to the the root mean squared value of the magnetic field squared over mu naught. And since it is squared, we can see that the root mean squared value squared is equal to the maximum value squared over 2. So there's a factor of 1/2 that shows up if we're relating it to the maximum value. And the same thing exists for the B field. Now, if we here's an interesting sort of result. If we rearrange, we've got this epsilon naught E squared, and that's equal to B squared over mu naught. If we rearrange this a little bit, we get and take a square root. If we solve for our electric field, we get that the electric field is equal to B over square root of mu naught epsilon naught. And 1 over square root of mu naught epsilon naught is just C. So, for an electromagnetic wave, the electric field and magnetic field are always related by this factor of the speed of light. So at any given time, you can take the magnetic field and multiply by C, and you'll get the value of the electric field. That's kind of an interesting result. Now there is a physical quantity that's very important with electromagnetic waves, and that's intensity. For visible light, the intensity tells you how bright a light is. Intensity is defined as an energy per area per time. So the intensity given to an area per time, well, it's energy per area times time. And that's just equal to, the energy is equal to the energy density times the volume. And the volume is equal to an area times, some length. Well, this wave is moving at the speed of light, and so the distance that it covers is equal to ct. And so kind of the length of wave that's hitting an area in a given time is equal to ct. So that's our volume, and that's over at. And so you notice that the a and the t cancel out. So the intensity is just equal to the energy density times the speed of light. Now notice energy per time is a power. So you could also say the intensity is equal to power over area. Right? And that's something that's going to be useful for solving some problems. So for a given time period, the average intensity is equal to the average energy density times C, which is equal to C times epsilon naught E root mean squared, which is equal to C times the root mean squared of the magnetic field over mu naught. So, that's a lot of equations all talking about energy. All of them are applicable. Really, though, you really need to know that. And this relationship is handy and interesting, but you might need it for a couple homework questions. And you really need to know that intensity is that. So really those two, there's a lot of stuff scribbled all over here. And I guess you need to know what root mean squared means. But there's not a ton on here that you need to memorize per se. So let's take a look at an example question that could apply this principle. I want to know what the root mean squared electric magnetic fields are 2.5 meters from a 60 watt light bulb. Well, we know intensity is equal to energy density times C, and if we want to find the E field, we'd probably want to use this. Okay. In this case, the average intensity is equal to the regular type intensity, just because the power output of the bulb is constant. And that's equal to the power of the bulb over the area. And now the area might seem a little problematic, but let's just stop and think about it for a second. If we've got a light bulb, then it's radiating out light in all directions. Okay, so the area that a given set of light rays are hitting at a time is passing through the surface of a sphere a set distance from the light bulb. And so 2.5 meters away, the surface area of a sphere is 4 pi times radius squared. So that's our intensity, 2.5 meters away, and we can use that to calculate the values of the root mean squared magnetic and electric fields. The root mean squared electric field is 60 over 4 pi times 2.5 squared all over c times epsilon naught, and the root mean squared B field, square root mean squared B field is square root of 60 mu naught over 4 pi 2.5 squared times c. And I can punch those values into my calculator, and I get a value of 16.96. Remember, electric field is newtons per coulomb or volts per meter. They're equivalent. And the magnetic field is 5.656, etc., times 10 to the minus 8th. Sorry, that's scrunched over there. I'm going to put it down here. 5.65 times 10 to the minus 8th Tesla. And if we look at these equations, and we can double check. If I take that 5.65 times c, I do get the value of the electric field, which is good because they should have that sort of relationship.